Hello, everyone. This is Niloy Biswas. I'm a graduate student doing a statistics PhD at Harvard. Today, I'll be speaking about coupling-based convergence assessment of some Gibbs samplers for high-dimensional Bayesian regression with shrinkage price. This is joint work with Anirban Bhattacharya, Pierre Jacob, and James John Rowe. To set up this talk, I'll first of all introduce high-dimensional Bayesian regression. Secondly, I will talk about a Gibbs sampler for a particular class of prize for Bayesian regression. Thirdly, I will talk about the importance of prior choice, both for statistical estimation and computation when it comes to sampling from this posterior. And lastly, I will highlight an empirical example showcasing our method in modern large-scale genome-wide association studies datasets. To begin with, let's set up high-dimensional Bayesian regression. We have data coming from n observations where the response is continuous. And we also have a design matrix X where the number of covariates per data point, denoted by P, is much larger than the number of observations. This is the high-dimensional regime. We focus on linear regression, where the response Y is modeled as a matrix product between X, the design matrix, and some vector B, where beta is unknown and the quantity we want to do inference on. And we have Gaussian noise. In the Bayesian setting, I'm going to focus on global, local, continuous shrinkage price, and in particular, half T shrinkage price. I've described the setup in this page. First of all, we have sigma corresponding to the noise from the linear regression. And then for our unknown components beta, we assign a prior, which depends on sigma, which depends on Kc, and which depends on eta j. Now, Kc is common in all beta j's and corresponds to the sparsity. Eta j is different for different components beta j, and will allow us to distinguish whether a particular component is a null signal or a significant signal away from zero. In particular, Kc correspond to the global part of the global local shrinkage price, and eta j's correspond to the local of the global local shrinkage price. We assign a gamma distribution on the sigmas. We assign a half Cauchy on the square root of 1 over the Kc, and also a half T distribution on the etas. In particular, in the case when this degree of freedom in a half T distribution is equal to 1, this prior corresponds to the popular Horseshoe prior that has been well studied and is commonly used. So Gelman has highlighted some of the reasons one may wish to use half T priors before, and there is follow-up work by Carvalho, Paulson, and Scott focusing on the Horseshoe as a desirable prior for Bayesian regression. Under this setup, I'm going to now highlight what the posterior distribution may look like for a very simple stylized example. So in this case, my number of data points is just 2, and my dimension is 3, and my unknown signal, so the truth, I've written as 100. So this is unknown. We only observe the design matrix X and Y. Now, how do the posterior densities look? You can see in these two-dimensional marginal plots. In each of these cases, you can see there are bimodalities present. And also there is a increase in density about 0, which I'll come on to. The motivation behind these figures to hide is that even in this very simple example, we can see that the posterior is highly multimodal. And this will continue to be the case even more so in higher dimensions. Now, to highlight some of the statistical benefits of such priors, if we integrate over the etas for our prior for beta, we find that the prior for beta has infinite density about 0 and has polynomial tails at infinity, where the degree of freedom nu tells us the tail of the polynomial. The exponent here should be minus 1 plus nu. Now, such priors have been shown to have statistical estimation benefits. There is a line of work by Van der Pas where the normal means model has been studied with these priors and shown to have nearly statistically optimal minimax properties in terms of the posterior contraction. And that's done for the Horseshoe, and Kosher and Chakraborty also highlights general results which cover priors such as the half T. Now, on the computation side, some of these desirable properties that come from statistical estimation actually lead to, first of all, numerical instability for gradient-based samplers. Because our density goes off to 0, goes off to infinity about 0, many popular gradient-based samplers run into numerical instability. And secondly, because we have polynomial tails, Gaussian proposal-based Metropolis Hastings samplers can converge very slowly and may no longer be geometrically ergodic. So this is to highlight the message in this setting that there is a trade-off between the posterior distributions that are statistically useful and generic sampling algorithms targeting these posterior distributions. And there is a motivation to consider tailored sampling algorithms for these settings. So this is what I'm going to highlight now by focusing on a Gibbs sampler targeting the posterior that I've just described. Now, for simplicity of this talk, I'm going to assume C and sigma are fixed. We allow these things to vary with details in the paper. These two are both real scalar quantities. Now, assuming these two things are fixed, our Markov chain is a Gibbs sampler, which is composed of 2 steps. Firstly, we have the beta given eta sampling step, which involves sampling from a p-dimensional Gaussian. Secondly, we have an eta given beta step, where each eta j given beta j are component-wise independent. So you can sample these real quantities p times independently. There is recent work focusing on the Horseshoe, which look into Gibbs samplers of this format. And in particular, the computation cost of such samplers can be reduced to n squared p, where n squared comes from the n is the number of observations and p is the dimension. Now, for the general half-T priors, we show that such Gibbs samplers are indeed geometrically ergodic. This involves some technical extensions to prior work, in particular the polynomial tails and the infinite density about 0 need to be taken into account. Now, in terms of assessing convergence, in this setting especially, it's extremely important for practitioners to understand whether the Markov chain has converged. The reasons being that this can be a very expensive chain to run. So each iteration has great computation cost. Therefore, running a chain longer than required may be very wasteful. And on the other hand, in a very high dimensional regime, we could be worried about not running a Markov chain for a sufficiently long number of time. The technique we will use to assess convergence is using couplings. In particular, I will focus on an earlier paper I've worked on, which I describe in an earlier presentation here. But Val and Johnson have also worked on coupling-based ideas for convergence too. Okay, now I'm going to describe a coupling for the marginal chain described before. So again, to emphasize, the single chain is a Gibbs sampler, which has two steps. The beta given eta step involves sampling from a high dimensional Gaussian. So here it's a p-dimensional Gaussian, where p corresponds to the number of covariates. The eta given beta step corresponds to sampling from p different eta j's, which are component-wise independent. Now, I'm going to introduce a coupling for this single chain. For anyone who is seeing this presentation for the first time, I recommend seeing the LLAC coupling presentation first to get some background. Now, the couple chain I'm going to propose will simply do common random numbers for the beta given eta step. So imagine we sample a p-dimensional standard normal, and then we apply a linear transformation to that p-dimensional standard normal such that marginally it follows the corresponding distributions from the single chains given eta 1 and eta 2. This is called a common random numbers coupling or a synchronous coupling also in the literature. Now, for the eta given beta step, I will do two different things depending on how close the chains are. When the chains are very far away, where by far away, I mean I introduce a metric d and I say the metric d is larger than some threshold value, d threshold. When the chains are far away, I will do common random numbers for each of the eta j steps too. So important thing to highlight here is that under common random numbers, because we're working in a continuous state space in each of these steps, the chains will never exactly meet. However, when the chains are very close, where I define close to be below some threshold with respect to some metric d that I'm yet to define, I will attempt max coupling. This is a type of coupling which allows two continuous distributions to exactly meet. So max coupling allows the eta j's to exactly meet between the two chains. Now, why might this particular coupling be a good idea, first of all? And secondly, which metric d is a good choice here to measure how close the two chains are to each other? Now, the insight informally is that when the two chains are far away with respect to some of this metric, attempting the etas to exactly meet can be wasteful, because when you fail, the chains can actually move further away from each other. Therefore, we should only attempt to meet when very close. And what do we mean by close? This is when we have to decide on our choice of metric d. We want d to capture the probability of exactly meeting, because failing to meet leads to the chains moving further away. And in particular, we choose our metric d to be exactly equal to the probability of all the etas, so that each of the p components for all of the eta vectors of exactly meeting. So this is related to the total variation distance of this step. Now, there is existing work from nearly 20 years ago. This is closely related to the delayed one-shot coupling of Roberts and Rosenthal, where such couplings were introduced for theoretical analysis in applied probability. In this paper, we look into actually designing algorithms which simulate such couplings directly. Now, to highlight some performance improvement, focusing on the horseshoe, you can see, so in this case, I have number of observations equal to 100. The dimension I increase from 50 to 150. You can see in the case when I try to maximally couple all the time, my coupling time taken for the two chains to exactly meet, seems to grow almost exponentially as I increase dimension, especially as dimension gets larger than the number of observations, where the number of observations is 100. In contrast, the two-scale coupling I've just described, where we only attempt maximal coupling and exact meetings when close, and common random numbers coupling when far away, the coupling times seem more scalable. So there is some promise in introducing this two-scale coupling empirically. Now, I'm going to recognize that I'm only working with 150 dimensions here. So can we do more? And here, to further extend our chains, the prior choice makes a huge difference. So first of all, I'm going to highlight the importance of this degree of freedom in our eta priors. So what is the impact of this degree of freedom nu for a half T prior statistically? So for this slide, just consider a synthetic dataset where I have 100 observations. The dimension of the number of covariates is 500. I consider a true beta, which has exponentially decaying signal and 20 non-null components. And I simulate the design matrix using IID Gaussians. Now, you can see the mean squared error on the figure on the y-axis. And on the x-axis, I show the error bars from 100 different simulated data sets for different values of degrees of freedom. You can see we start at 1, which corresponds to the horseshoe. As you increase the degree of freedom from 1 to all the way up to 2, the mean squared error does not drastically change. There is no statistically significant increase. But only as you get to much higher degrees of freedom, our mean squared error worsens. And in particular, what's going on here is that higher degrees of freedom correspond to more concentrated priors. So if you keep increasing the degree of freedom by making the prior more and more concentrated, eventually you may no longer be able to find the non-null signals, as is the case, for example, when degrees of freedom is equal to 6 or 8. Now, to compare this with the lasso, for example, you can see for degrees of freedom 1 to 2, we perform more favorably in terms of mean squared error in comparison to the lasso. Here, the lasso parameters are chosen optimally using cross-validation. So takeaway from this slide, small change in the degree of freedom does not empirically degrade the mean squared error performance. And it seems to do better than the lasso for smaller degrees of freedom. Now, on the computation side, we can look at the coupling times when you vary this degree of freedom. So I'm using the LLAC couplings that are in an existing paper that I've also given a presentation about here. And you can see, for example, the line in purple showing the slow convergence for degree of freedom 1. Here, I'm working with 500 dimensional covariates. And in contrast, you can see when I go to degree of freedom 2, my total variation distance upper bounds go to zero much, much more quickly. Similarly, to highlight the same idea, you can see that the meeting times appear to be much, much more scalable in higher dimension for higher degrees of freedom 2 compared to the horseshoe corresponding to degrees of freedom 1. This motivates using a larger degree of freedom greater than 1. There seems to be order of magnitude improvement in coupling times or meeting times, but actually comparable statistical performance. And we summarize these two ideas in the two figures shown. You can see on the left-hand side, the mean squared error staying roughly similar for different degrees of freedom. But on the right-hand side, the meeting times can drastically decrease with higher degrees of freedom. So this overall motivates using larger degrees of freedom nu. Now, to highlight an example of our coupling-based diagnostics with the half T prior working with degree of freedom 2, I look at a genome-wide association studies dataset with 2,000 observations and nearly 100,000 covariates linked to SNPs in the genome. So now our Markov chain is in this 200,000 dimensional state space. And we can ask the question, how long does it take to converge? And empirically assess this question using couplings. And the plot shows, using this 2-scale coupling I've just described, our Gibbs sampler can converge in less than 1,000 steps. So this is, again, a vindication of both couplings in such high-dimensional settings, but also Markov chain Monte Carlo methods in general for such high-dimensional settings. And something to emphasize here is that if one were to use something like trace plots, it would be very difficult to try to assess Markov chains which are 200,000 dimensional. Practically, it will take an impractical amount of time to assess each of these trace plots. So couplings in general give a simple upper bound of total variation distance, even in such challenging large-scale Bayesian inference problems. So the reference for this paper is, again, coupling-based convergence assessment of some Gibbs samplers for high-dimensional Bayesian regression with shrinkage prides. It's available on arXiv and currently under review. And the code which has been optimized to work in large data sets is all available online. So we have a package. Thank you.